Okay, today we're going to be talking about the power winch and skier problem. So in the question they give us four statements, that the skier weighs 27.4 kilograms, he's on a 29-degree incline, the surface friction coefficient between him and the ground is 0.03, and he's moving at 1.7 meters per second. The question is, how much power does the winch at the top take to pull him up the hill? So let's write down some formulas that we're going to need. So the power formula is power in watts equals work over the change in time. And the work formula is the force over the change in distance. So now that we know that, we need to find the force of the winch. So let's draw ourselves a little free body diagram here. That dot in the middle is the skier. Force of gravity is pointing downwards, and force of gravity equals the mass times acceleration. The acceleration is 9.81 in everything that's on Earth. Our normal force is our force of gravity times cosine of the incline. Our friction coefficient is, our friction force is the normal force times the friction coefficient. And so when we do all those calculations, we get force of gravity is 268 newtons, normal force is 235 newtons, and friction force is 7.05 newtons. So what I did is I just rotated this 29 degrees clockwise, so it'd be a little bit simpler. So we know that the cosine part of force of gravity and normal force cancels out. So, and because the skier is moving at a steady speed, we know that the net force is equal to 0. So, we need to find the force of tension. It's going to cancel out the friction force and the sine theta of the force of gravity. So that equals 137.367 newtons. And so now that we have the force, we can move on to the next stuff. So work equals force times the change in distance. And so just for the sake of simplicity, I set the distance to 10 meters, and that gives us 1,373.67 joules of work. And power equals work times the change in time. And so it takes 5.882 seconds to go 10 meters at a speed of 1.7 meters per second. And so we just divide work by the time of 5.822 seconds. That gives us a power of 233.52 watts.